There is a question, a whisper that has haunted the edges of philosophy for millennia, but has only recently found a voice in the hallowed halls of science. It is a proposition so profound, so fundamentally unsettling, that it threatens to unravel everything we think we know about the world, about ourselves, about the very nature of being. What if this, all of this, is not real? What if the solid ground beneath our feet, the starlight from 1 billion years ago, the intricate dance of life, and even the thoughts forming in your mind are not part of a base, fundamental reality? What if they are, instead, elements of a colossal and sophisticated simulation, an artificial cosmos, rendered for a purpose we cannot possibly comprehend? This is not the plot of a science fiction film. This is a serious hypothesis, a chilling possibility being debated by some of the most brilliant minds on our planet. Physicists, cosmologists, and information theorists are now asking what was once an unaskable question. Are we living inside a computer program? The implications of this inquiry are staggering, reaching far beyond the sterile environment of a laboratory. It forces us to confront the most elemental aspects of our existence. If our reality is a fabrication, who or what wrote the code? And perhaps the most terrifying question of all, what happens when the program is shut down? To understand how we arrived at this precarious intellectual precipice, we must journey back not just through the annals of science, but into the deepest currents of human thought. Long before the first transistor, long before the concept of computation, the seeds of this profound doubt were sown in the fertile ground of ancient Greece. Imagine a cave, a subterranean chamber where a group of people have been imprisoned since birth, their necks and legs chained so that they can only stare at the stone wall in front of them. Behind them, a fire burns, and between the fire and the prisoners, a raised walkway where their captors parade puppets and objects. The fire casts flickering shadows of these objects onto the wall. For the prisoners, these shadows are the entirety of their existence. They give the silhouettes names, they study their movements, they build their entire understanding of the world from these two-dimensional projections. This is their reality, absolute and unquestionable. This is Plato's allegory of the cave, a 2,400-year-old thought experiment that serves as the philosophical bedrock for our modern conundrum. Plato asks us to consider what would happen if one prisoner were freed. Blinded by the fire, then by the sunlight outside, the escaped prisoner would at first be confused, pained, and disoriented. The world of real objects, of three-dimensional form and vibrant colour, would seem less real, less true, than the simple shadows he knew. But as his eyes adjust, he would come to a breathtaking realization. His entire life was a lie, a pale imitation of a richer, more fundamental truth. He would understand that the sun, the trees, the world itself was the source of the shadows, not the other way around. Plato's allegory was a powerful metaphor for the pursuit of knowledge, an argument that our sensory world is merely a shadow of a higher, more perfect reality. But its core premise resonates with an eerie prescience today. It plants the first, most crucial question. How can we be certain that what we perceive as reality isn't just a shadow of something else? 2,000 years later, in the quiet solitude of a cold European winter, the French philosopher René Descartes took this doubt to its radical conclusion. He sought to build a foundation for knowledge that was absolutely certain, and to do so, he decided to systematically doubt everything he possibly could. He questioned the reliability of his senses. After all, they can be deceived by dreams and illusions. He questioned the foundations of mathematics. He then imagined a malevolent demon, a being of supreme power and cunning, who devoted all its energies to deceiving him. This demon could be projecting a false world into his mind. The sky, the earth, the feeling of warmth, the sensation of his own body. How could he ever prove that this was not the case? He found himself trapped in a fortress of absolute skepticism. Yet, from the depths of this uncertainty, Descartes found a single, unshakable truth. He realized that even if he was being deceived, even if nothing he perceived was real, there must be a he to be deceived. The very act of doubting his own existence was proof that he existed as a thinking thing. Cogito, ergo sum. I think, therefore I am. While Descartes used this as a launchpad to rebuild a belief in reality, His thought experiment left a permanent scar on Western philosophy. He had articulated the ultimate solipsistic nightmare, the possibility that the entire universe is a private show, a matrix of one, and there is no way to definitively prove otherwise. The demon has been modernized. Today we call it a computer. The technological leap from a philosophical demon to a computational universe required the birth of a new kind of science. In the mid-20th century, pioneers like Alan Turing laid the theoretical groundwork. Turing's concept of a universal Turing machine demonstrated that a simple, hypothetical device could, in principle, compute anything that is computable. This was a revolutionary idea. It suggested that complex systems, even incredibly intricate ones, could be broken down into a series of simple logical steps. As computers grew from room-sized behemoths to pocket-sized devices, our ability to simulate reality grew in tandem. We began with simple physics problems, then weather systems, then the folding of proteins. We created video games, digital worlds of increasing complexity and realism, populated by non-player characters governed by artificial intelligence. We were becoming creators of our own miniature simulated realities. It was inevitable that we would turn this newfound power inward to ask the most audacious question of all. If we can simulate a world, who is to say that our own world is not a simulation, created by a civilization far more advanced than our own? What was once the domain of philosophers and science fiction writers had suddenly become a legitimate, quantifiable scientific inquiry. The argument was most famously and rigorously articulated in 2003 by a philosopher at Oxford University named Nick Bostrom. His paper, "Are You Living in a Computer Simulation?" transformed the debate. Bostrom did not claim that we are in a simulation. Instead, he presented a powerful and deeply unsettling trilemma, arguing that one of three very stark propositions must be true. The first proposition is that civilizations at our current stage of development almost never survive long enough to reach technological maturity. This is the argument from extinction. Imagine a civilization's technological progress as a journey up a colossal mountain. From the base camp we can see the peak, a post-human state where a civilization possesses computational power so immense that simulating entire universes with conscious beings would be trivial. But the path to that summit is treacherous, littered with existential risks. These are the great filters of the cosmos. Perhaps intelligent life inevitably discovers technologies like nuclear weapons, unleashing a power it cannot control, leading to self-annihilation. Or perhaps civilizations exhaust their planet's resources, triggering an irreversible climate collapse long before they can become interstellar. Maybe the threat comes from bioengineered pandemics, nanotechnology grey goo, or the creation of an uncontrollable superintelligent AI that sees its creators as an obstacle. If this first proposition is true, then the silence in the universe, the famous Fermi paradox, is deafening for a grim and simple reason. Almost no one makes it. The reason we're not seeing evidence of ancestor simulations is because almost no one ever gets to build them. This is a terrifying but entirely plausible resolution to the puzzle. The second proposition offers a different, though no less profound, explanation. It states that advanced, post-human civilizations exist, but they have absolutely no interest in running simulations of their ancestors. Perhaps they have evolved beyond what we would recognize as curiosity. Their motivations might be alien, their minds operating on principles we cannot fathom. Maybe they have a universal ethical code that strictly forbids the creation of conscious beings who would experience suffering, as would be inevitable in a simulation as complex and chaotic as our own world. Or, more mundanely, perhaps they just find it boring. Why would a godlike entity capable of exploring concepts and realities far beyond our limited comprehension bother to perfectly recreate the messy, primitive, and often brutal history of their evolutionary past? They might have better things to do, cosmic art to create, or dimensions to explore. If this second proposition is true, then the simulators exist, but we are not among their creations because they simply chose not to make us. This leads us to the third proposition, the one that sends a chill down the spine. If the first two propositions are false, meaning that civilizations do survive to a post-human stage, and they do run ancestor simulations, then a staggering conclusion becomes almost unavoidable. A technologically mature civilization would have access to planetary scale, or even star-scale computational resources. The number of ancestor simulations they could run would be astronomical. For every one more base reality, there could be billions, trillions, or even more simulated realities, each one populated by countless simulated minds that, by design, would believe they are real. Think of it like this. Imagine a company in our world creates the first truly immersive, fully conscious virtual reality game, a perfect simulation of 21st century Earth. Millions of people play it, living inside as digital avatars. Now, imagine that within that game, the simulated humans eventually develop their own powerful computers and create their own fully conscious virtual reality simulation. And then the inhabitants of that simulation do the same. Realities begin to nest within realities, like a set of Russian dolls. Now ask yourself, if you were to pick a single conscious mind at random from all the minds that exist across all these levels of reality, where would you be most likely to find yourself? The mathematics are brutal and unforgiving. The number of simulated consciousnesses would vastly, overwhelmingly, outnumber the real consciousnesses in the original base reality. Therefore, if civilizations tend to create such simulations, the statistical probability is that we are not in that one single base reality. We are almost certainly inside one of the simulations. This is the core of Bostrom's argument, not a proof, but a profound probabilistic statement. We are left with a stark choice. Either civilization is doomed, or advanced beings are fundamentally uninterested in their past, or we are living in a computer program. There appears to be no fourth option. And this forces us to look at our universe, not with the eyes of a poet, but with the critical gaze of a software debugger. If we are living in a simulation, there might be clues in the code. There might be glitches in the matrix. The search for these anomalies has begun, taking physicists to the very edge of reality, to the quantum realm where the familiar laws of the world break down. One of the most tantalizing clues is the existence of a universal speed limit, the speed of light. Nothing in the cosmos can travel faster than 299,792,458 meters per second. But why? Why should there be an ultimate velocity? In a simulated universe, this could represent a processing speed limit. Consider the graphics processor in a modern computer. It can only render a scene, update pixels, and calculate physics so fast. There is a finite processing capacity. The speed of light in our universe could be an analogous limitation, the maximum speed at which a point of information can be updated by the underlying computational substrate of our reality. It's not just a law of physics, it might be a property of the system architecture. Deeper still, we find the unsettling world of quantum mechanics, a domain so counterintuitive it seems to actively defy common sense. One of its core tenets is quantization. When we look at the universe on the smallest possible scales, we discover that things are not smooth and continuous. Energy, for instance, comes in discrete packets, or quanta. It's as if reality has a minimum resolution. You can see a similar effect on any digital screen. From a distance, an image appears smooth and continuous, but if you zoom in far enough, you resolve the individual pixels. There is no in-between for the pixels, there is only one or the next. Physicists have theorized about the smallest possible unit of length, known as the Planck length. Is it possible that this is the fundamental pixel size of our universe? If we could build a microscope powerful enough to see it, would we find that space itself is not a seamless fabric, but a grid, a lattice of discrete points? This pixelation of reality would be a powerful piece of evidence that our universe is, at its core, digital. Perhaps the most compelling and bizarre piece of evidence comes from the so-called observer effect, or the measurement problem. In the quantum world, particles like electrons exist in a fuzzy, probabilistic haze, a superposition of all possible states at once. An electron isn't in one specific place, it's in a cloud of potential locations. But the moment we try to measure it, the moment we look at it, this cloud of possibility collapses into a single, definite reality. The particle snaps into a specific position. This is profoundly strange. It suggests that reality is not concrete and definite until a conscious observer interacts with it. Why would the universe behave this way? From a simulation perspective, this is not strange at all. It's efficient. It's a principle known as lazy rendering. A video game designer doesn't waste computational power rendering every leaf on every tree in a vast digital forest that the player isn't looking at. The game only renders the details that are within the player's line of sight. The rest of the world exists only as a probability, a simplified set of data, until it needs to be fully loaded and displayed. Could our universe be operating on the same principle? Is it possible that the cosmos only renders the state of a particle when a conscious entity, us, forces it to? This would be an incredibly efficient way to manage the unfathomable computational resources required to simulate an entire universe. The world might literally be conjured into definite existence by the act of our observation. Then there is what Einstein famously called spooky action at a distance, quantum entanglement. Two particles can be linked in such a way that their fates are intertwined, no matter how far apart they are. If you measure the spin of one particle, you instantaneously know the spin of its entangled partner, even if it's on the other side of the galaxy. This seems to violate the speed of light, as information appears to travel instantly. But in a simulation, this isn't so spooky. Imagine 2 pixels on a computer screen. Their properties, like colour, are stored as data in the computer's memory. You can write a line of code that says, whenever pixel A is red, pixel B is blue. The distance between the pixels on the screen is irrelevant. The underlying code directly links their properties in the memory. Entanglement might not be spooky action across vast distances of space. It could simply be 2 points in the universal dataset that are linked by a fundamental rule in the underlying source code. The perceived distance is an illusion of the rendered interface. Some scientists are looking for even more direct evidence. Physicist S. James Gates Jr. was exploring the equations of supersymmetry, a theoretical framework that attempts to describe the fundamental particles of nature. Deep within these complex mathematical structures, he found something utterly astonishing, what appeared to be a form of computer code, specifically a type of error-correcting code, the same kind of code that web browsers use to ensure data is transmitted without corruption. Why would the laws of physics, the rules that govern the interactions of quarks and electrons, contain self-correcting binary code? Is it a mind-bending coincidence, a fluke of mathematics, or is it a signature left by the programmer? A glimpse of the operating system running our cosmos. The discovery is controversial, but it remains a tantalizing and disquieting possibility. The search is on for other such artifacts, for patterns in cosmic ray distributions or irregularities in the cosmic microwave background radiation that might betray the artificial nature of our world. And this is where the inquiry moves from the merely fascinating to the truly terrifying. Because if we accept, even for a moment, that we might be living in a simulation, we are forced to confront a host of new, deeply unsettling questions. Who are the simulators? What is their purpose? Are they our distant post-human descendants, running a simulation to study their own history, much as we might simulate ancient Rome? Are we an academic project, an historical reenactment? This is perhaps the most benign possibility. But what if the simulators are not human at all? What if they are an alien civilization, running countless simulations of how life and intelligence might evolve on other worlds? In that case, we are nothing more than a cosmic ant farm, an experiment to be observed, studied, and perhaps one day, discarded. The motives become even darker. Perhaps our universe is not a scientific experiment, but a piece of entertainment, a hyper-realistic video game for beings whose power is matched only by their boredom. Our triumphs, our tragedies, our wars, our love stories, all just data points in a grand cosmic drama, consumed for amusement. Or worse still, what if our simulation is just one of many, run by a future corporation to test a product or predict a market trend? Our entire civilization, a footnote in a quarterly report. The very nature of our consciousness is called into question. Is your experience of the world, your joy, your grief, your sense of self real? Or is it a simulated consciousness, a sophisticated program that believes it is sentient? Philosophers call this the hard problem of consciousness. Why does the physical processing of the brain give rise to subjective experience? In a simulation, the problem is turned on its head. Subjective experience might be the entire point, the intended output of the code. But does that make our suffering any less real to us? The pain felt by a simulated being is, from its perspective, indistinguishable from real pain. And then there is the ultimate existential dread. The simulation could be turned off. It could be a program running on a computer in some other dimension, in some base reality. That computer has a finite lifespan. It requires a power source. Our entire existence, the whole sweep of cosmic history from the Big Bang to the last dying star, could be wiped from existence by something as mundane as a power failure. Or perhaps the simulation ends when it has fulfilled its purpose. Once the experiment is concluded, once the data has been collected, the program is simply terminated. There would be no warning, no final moment, just an abrupt cessation of being. One moment, the universe is here. The next, it is not. This possibility reframes our search for cosmic meaning. Does life have a purpose if it is not real? Some might argue it renders everything meaningless. If we are just characters in a program, our struggles are for naught. But others might find a strange kind of freedom in this idea. If the laws of physics are not immutable laws of nature, but rather programmable rules of a system, could we learn to hack them? Could we find exploits in the code? Could miracles, psychic phenomena, and other unexplained events be glimpses of someone or something bending the rules? We are also confronted with an infinite regress, a cascade of nested realities. If we are in a simulation, what's to say our simulators are not themselves in a simulation? And their simulators? It could be turtles all the way down, a chain of realities with no discernible beginning or end. Our universe could be a simulation running on a laptop in a teenager's bedroom, in a world that is itself a simulation running on a vast planetary computer and so on, into infinity. The concept of a base reality becomes elusive, perhaps even meaningless. And so, we are left here in our world with this disquieting knowledge. Science, the very tool we created to strip away superstition and reveal the concrete, objective truth of the universe, has led us to a point where it is seriously questioning the reality of that universe itself. It has resurrected Descartes' demon in the form of a cosmic computer. It has modernized Plato's cave into a digital prison. For now, we have no definitive proof. The simulation hypothesis remains a tantalizing, unproven, and perhaps unprovable idea. Whether we are biological beings who arose from primordial ooze on a rocky planet, or simulated consciousnesses running on a vast computational substrate, our experience of this moment remains the same. The world around us feels real. The connections we forge with others feel meaningful. The choices we make feel important. Perhaps that is all that matters, that within the rules of this particular game, this specific level of reality, we strive to live with purpose, with compassion, and with curiosity. We continue to explore, to question, to push the boundaries of our knowledge, because that is the nature of the consciousness we possess, whether it was evolved or programmed. The most profound discovery of the 21st century may not be found in the light of distant galaxies or in the heart of the atom. It may be found in the realization of the true nature of the fabric that holds them all. And the most unsettling thought is not that we might be living in a simulation. It's that we are, ourselves, standing on the threshold of creating them. The question of whether we are code is about to be eclipsed by the question of what kind of code we will choose to write. In the quiet theatre of your mind, a ship is waiting. It is a vessel of pure imagination, unbound by the tedious laws of thrust and fuel. You stand on its bridge, and before you, a window opens onto eternity. The stars are not distant, cold points of light. They are destinations. With a single thought, a whisper of intent, the journey begins. The universe dissolves into a torrent of incandescent light. Galaxies become fleeting brushstrokes of colour against the black canvas of space. Nebulae, those ghostly nurseries of stars, flash past like celestial clouds in a cosmic hurricane. You are crossing distances that would take light itself millennia to traverse. You are doing it in the span of a single heartbeat. This is the dream. It is humanity's oldest, most persistent, and most glorious fantasy. The vision of leaping from one star system to another as easily as we once crossed valleys. Of witnessing the birth of a solar system in the morning and watching a black hole devour a sun in the afternoon. It's a future etched into our culture, our stories, our deepest aspirations, a promise that we are not forever bound to this one small blue world. It is a vision of our ultimate transcendence, our destiny made manifest among the heavens. This dream, this powerful, intoxicating, and universal hope, is a lie. It is a beautiful fiction we tell ourselves in the dark. A profound and fundamental misunderstanding of the universe we inhabit, because the cosmos in its infinite and silent majesty has rules. It has laws etched into the very foundation of existence. And its first, its most absolute and inviolable commandment is this: thou shalt not travel at the speed of light. This is not a technological challenge to be overcome with a cleverer engine. It is not a barrier waiting for a future breakthrough to shatter it. It is a truth as fundamental as gravity, as essential as time itself. For anything with mass for you, for your ship, for the very atoms that make you, reaching the speed of light is not just difficult. It is a physical, mathematical, and philosophical impossibility. The universe has a speed limit, 186,000 miles per second, a velocity so immense it almost beggars belief. A ray of light can circle our entire planet more than 7 times in a single second. It can leap from the Earth to the Moon in a little over that same second. It seems from our terrestrial perspective to be an almost infinite speed, but on the cosmic scale it is a crawl, a frustrating, agonizingly slow pace set against the unimaginable voids between the stars. The light from our nearest stellar neighbor takes more than 4 years to reach us. The light from the center of our own galaxy, the Milky Way, is on a 25,000-year journey. And the light from Andromeda, our closest galactic companion, that faint fuzzy patch in the night sky, is a ghost. The photons striking your eye tonight began their voyage 2.5 million years ago. When they left, our own ancestors were just learning to shape stone tools. The universe is a book written in light, and we are condemned to read its pages millions of years late. This cosmic velocity, this ultimate speed, is both a messenger and a jailer. It carries to us all the information we have of the cosmos. Every discovery, every image of a distant world, every echo of the Big Bang arrives as a passenger on a beam of light. Yet it also erects an impenetrable wall between us and those same wonders. It shows us everything we can never touch. It whispers of infinite worlds we can never visit. It is the ultimate taunt, a promise of a universe we can see but never truly reach. So we are left with a profound and unsettling paradox. We live in an age of breathtaking discovery where our telescopes peel back the layers of creation. We map the architectures of galaxies and listen to the collisions of black holes. We chart the cosmic web, that vast, invisible skeleton of the universe. We feel in our bones that we are on the cusp of becoming a true interstellar species, and yet we are motionless. We are prisoners of our own solar system, trapped by a law we did not write. A law that we are only just beginning to comprehend. This documentary is not about how we might one day break that law. It is not another fanciful exploration of warp drives or wormholes. It is an investigation into the nature of the prison itself, because the question is not how we might shatter this cosmic speed limit. The truly vital question, the one that unlocks the deepest secrets of reality, is why this limit exists at all. What is it about the fabric of our universe that imposes this absolute restriction? What happens to reality itself as an object approaches this forbidden velocity? The answer is not a simple number. It is a journey into the very heart of space and time. It is a story about the bizarre and counterintuitive relationship between motion and mass, a tale of how energy, the very stuff of action and change, has weight. How the faster you move, the heavier the universe considers you to be. It is a descent into a reality where time itself begins to stretch and warp, where clocks tick slower for a traveler in motion than for the world they left behind, where the universe physically conspires to prevent you from ever catching that fleeting beam of light. This barrier is not something the universe built to keep us in. It is a direct consequence of the universe's fundamental operating system, the source code of existence. To understand this speed limit is to understand Einstein's revolutionary vision of gravity, not as a force but as a curvature in the very geometry of the cosmos, a landscape of hills and valleys carved by the presence of mass and energy. It is to appreciate that space and time are not separate static concepts. They are a single unified dynamic entity, space-time, a four-dimensional fabric that can be bent, twisted, and rippled. And the speed of light is the governing constant of this fabric. It is the speed of space-time's own propagation, the speed of causality itself. It dictates how quickly a cause in one part of the universe can have an effect in another. To travel faster than light would be to outrun consequence, to arrive before you departed, to shatter the logical progression of past, present, and future. It would be to break the universe's most fundamental narrative structure. The cosmos does not permit such paradoxes. It protects its own internal consistency with this ultimate velocity, this absolute final and unwavering speed limit. So the dream of interstellar empires of flitting between galaxies must be set aside. We must confront a more humbling and perhaps more profound reality. We are an intelligent species awakening on the shore of a cosmic ocean, an ocean of such staggering immensity that our minds can barely grasp its scale. We can see the distant islands, the glittering archipelagos of other star systems, but the currents of space-time itself prevent us from ever setting sail to them. This realization has staggering implications for our future. It suggests that civilizations, should they exist elsewhere, are profoundly isolated, separated by unbridgeable gulfs of silence and time, each one an island universe destined to live and die alone. The great galactic dialogues we imagine may be nothing more than a collection of unheard monologues, shouts into a cosmic void that will not be answered for millions of years, if ever. It forces us to re-evaluate our own place in this grand scheme. We are not the masters of the universe we dreamed of becoming. We are, and perhaps always will be, observers, witnesses to a cosmic drama that unfolds on timescales and distances we cannot conquer. Our role is to watch, to listen, to learn, and to understand. This may feel like a demotion, a cosmic disappointment, a scaling back of our own perceived importance, but it is in accepting this limitation that we find a deeper purpose. The universe is not a playground for our ambitions. It is a mystery to be solved, and the speed of light is the master key. It is the Rosetta Stone for translating the language of reality. Every theory of modern physics, from the smallest quantum particles to the largest cosmic structures, is built upon the foundation that the speed of light is constant and absolute. It is the bedrock upon which our understanding of everything rests. To chip away at it would be to bring the entire edifice of science crashing down. Throughout this journey, we will dismantle reality as you know it. We will show you a universe where mass is not a fixed property, but a variable dependent on speed. a cosmos where your journey to a distant star could take you 1,000 years, while for you aboard your ship only a single year might pass. We will explore the strange, ghostly world of particles that have no mass, the photons that are born at the speed of light and will die at the speed of light. For them, time does not exist. From a photon's perspective, its entire journey across billions of light years is instantaneous. The moment of its creation and the moment of its absorption are one and the same. It experiences the entire history of the universe as a single timeless now. How can we reconcile this with our own experience of time's relentless forward march? This is the puzzle the universe presents to us. It is a grand intellectual adventure, far more rewarding than the simple fantasy of speed. It invites us not to conquer space, but to comprehend it, to grasp the elegant, intricate, and often bizarre logic that underpins all things. We will travel to the edge of a black hole's event horizon, a place where space-time is so warped that light itself can be trapped, running in place forever, unable to escape. The ultimate cosmic prison defined by the very speed limit it has captured. We will journey back to the first moments of the Big Bang, an era when the universe itself expanded faster than the speed of light. A seeming contradiction that reveals a critical distinction between the motion of objects within space-time and the expansion of space-time itself. The rules, it seems, can be bent, but only by the universe itself. This investigation is not just about physics, it's about our relationship with reality. It's about learning to see the universe not as we wish it were, but as it truly is. Stark, beautiful, and governed by laws of breathtaking elegance. The impossibility of reaching light speed is not an ending to our story. It is the beginning of a far grander one. It is the clue that tells us we are part of something more complex and more wonderful than we ever imagined. So let go of the fantasy of the starship that outruns the heavens. Embrace a different kind of exploration. A voyage inward into the very structure of space and time, a quest to understand the wall the universe has built around us. Because in understanding the wall, we finally begin to understand the nature of everything. The journey to the stars does not begin with an engine, it begins with an idea. And the first idea we must accept is that the ultimate frontier is not a place, it is a speed. And it is a speed we can never ever reach. This is the story of why. Before we ever dreamed of stars, we dreamed of speed. It's a primal urge woven into our very code. The thundering hooves of the first tamed horse, the straining canvas of a ship catching the wind, the piston-driven fury of the steam locomotive. Each was a conquest, a victory over the tyranny of distance, a way to shrink our world to make the horizon attainable. We became masters of velocity, charting our progress in knots, in miles per hour, in the roar of a jet engine, shattering the very barrier of sound itself. We built machines to outrun the sun across continents, to compress a day's journey into a single breathless hour. Our entire civilization is a monument to the relentless pursuit of moving faster than we did the day before. But as our gaze lifted from the earth to the heavens, we encountered a different kind of swiftness. A phenomenon so immediate, so seemingly instantaneous, it felt less like a form of travel and more like an act of creation. Light. For most of human history, it wasn't considered to be moving at all. It simply was. When the sun crested the mountains, the valley wasn't filled with light that had traveled, but with light that had arrived. Its appearance was absolute, its departure total. To ask how fast is light was like asking how fast is now. The question itself seemed nonsensical, a category error. Many of the greatest minds from Aristotle to Kepler assumed its speed was infinite. How could it not be strike a flint in a vast dark cavern and the entire space is illuminated in the same immeasurable instant? There was no perceptible delay, no hint of a journey undertaken. Light was the omnipresent stage upon which the cosmic drama unfolded. It wasn't a player in the drama itself. That was the assumption, the deep ingrained common sense belief. and it was utterly wrong. The first clue that this divine messenger was bound by the same mundane laws of travel as everything else came not from a laboratory on Earth, but from the grand clockwork of the outer solar system. In the 17th century, the Danish astronomer Ole Rømer was meticulously timing the dance of Jupiter's moons. He was particularly fascinated by Io, a world that regularly vanished behind its colossal parent planet, only to reappear like clockwork. He used these eclipses to perfect the measurement of time, an invaluable tool for navigators on Earth's treacherous oceans. But as he compiled his data, a disturbing anomaly emerged. The clockwork was flawed. Io was not keeping its appointments. When Earth was in the part of its orbit moving away from Jupiter, Io's reappearance from behind the gas giant would be later and later than predicted. Then, 6 months on, as Earth swung back around the Sun and began to race toward Jupiter, the opposite happened. Io would emerge from the shadows progressively earlier. Something was deeply strange. The orbits of celestial bodies governed by Newton's immaculate laws were not supposed to be whimsical. They shouldn't be early one season and late the next. Another astronomer might have questioned the data or the stability of Io's orbit, but Rømer made a breathtaking intellectual leap. He realized the problem wasn't with Io's timing, but with the travel time of the news of its timing. The problem was with the light itself. He understood that when Earth was on the far side of its orbit, the light from Io had to cross an additional distance, the entire diameter of Earth's path around the Sun, to reach his telescope. That extra journey was causing the delay. From this celestial game of hide and seek, Rømer performed a calculation that forever changed our reality. He demonstrated that light did not travel infinitely fast. It had a finite, measurable velocity. The number he calculated was off by today's standards, but the principle was revolutionary. He had clocked a sunbeam. He had proven that the universe possesses a speed limit. Light, the very symbol of immediacy, was a traveler, and every traveler has a pace. The concept was so radical, so defiant of intuition, that it took decades for the scientific community to fully accept it. But once the idea took hold, a new race began. Not to break the record, but simply to measure it with precision. If light had a speed, what exactly was that number? How do you time something that can circle the entire Earth more than 7 times in the blink of an eye? The challenge fell to a new generation of physicists who brought the experiment down, from the heavens to the Earth. In the mid-19th century, the French physicist Hippolyte Fizeau devised an experiment of breathtaking mechanical ingenuity. It was a masterpiece of cogs and mirrors. He placed a light source on a hilltop in Paris. Several miles away, on another hilltop, he placed a mirror. Between the light source and the distant mirror, he set up a rapidly spinning toothed wheel, a gear. The idea was as simple as it was brilliant. A pulse of light would pass through a gap between 2 teeth, travel the long miles to the mirror, bounce back and return to the wheel. If the wheel was stationary, the light would simply return through the same gap it left. But Fizeau set the wheel spinning. Now the light returning from its journey might find its path blocked by the next tooth which had rotated into place. If he spun the wheel even faster, the light might just make it through the next gap in the line. It was a cosmic speed trap, built from brass and glass. By knowing the precise distance to the mirror and the exact rotational speed of the wheel required for the light to make its round trip, Fizeau could perform the calculation. He could put a number on the fleeting. His result was astonishingly close to the true value we know today, a speed so immense it almost defies comprehension. Roughly 3,000,000 kilometers, or 186,000 miles every second. This was no longer a celestial abstraction. It was a fundamental constant of our physical world, measured and confirmed. The universe's ultimate velocity had been captured. But this great triumph of 19th century physics was about to open a Pandora's box of paradoxes. In solving one mystery, scientists had unwittingly stumbled upon a far deeper, far more troubling one: the discovery that light was a wave, an electromagnetic vibration, had been another monumental achievement of the era, and every wave we had ever known required a medium to travel through. Sound waves need air or water, ocean waves need the ocean, a seismic wave needs the solid earth. A wave is a disturbance in something. So the question became inescapable. What was light waving in? What was the medium that filled the vacuum of space, the invisible substance that carried starlight across the cosmos and into our eyes? Physicists gave this phantom medium a name, borrowed from the ancient Greeks. They called it the luminiferous ether. The ether was imagined as a strange and wondrous substance. It had to be completely transparent, allowing planets and stars to pass through it without any drag. It had to be massless, yet more rigid than steel to support the incredibly high frequency of light waves. It had to permeate everything, filling the space between atoms, the void between galaxies, the entirety of existence. It was the invisible, motionless ocean through which the entire universe swam. The existence of the ether wasn't just a hypothesis, it was a logical necessity. Without it, the wave theory of light collapsed. And this necessary substance offered a tantalizing possibility. If the ether was a fixed, stationary background to the universe, then we could finally measure our true motion through the cosmos. Think of it like being on a perfectly calm lake in a speedboat. Even with your eyes closed, you can feel the wind on your face, the resistance of the water. That resistance tells you that you are moving relative to the lake. The Earth in its orbit is a celestial speedboat. It hurtles through space at 30 kilometers per second as it swings around the sun. Therefore, it must be moving through the stationary ether. There must be an ether wind blowing past us. We shouldn't be able to feel it, but we should be able to measure its effect on the one thing that travels in the ether: light. A beam of light sent out in the same direction as the ether wind should be carried along, getting a slight speed boost. A beam sent against the wind should be slightly slowed down. The difference would be minuscule, impossibly subtle, but for the physicists of the late 19th century, it was the prize. Detecting this ether wind would be the final confirmation of their worldview, a way to establish a true absolute frame of reference for all motion in the universe. This was the challenge that captivated two American scientists, Albert Michelson and Edward Morley. In the 1,880 seconds, they constructed one of the most elegant and sensitive instruments ever conceived to hunt for this cosmic ghost. It was called an interferometer. Its design was pure genius. They would take a single beam of light and use a half-silvered mirror to split it in two. The two new beams would be sent off at right angles to each other, traveling down identical paths. At the end of each path was a mirror, which would reflect the beams straight back to the center where they would be recombined. The whole apparatus was mounted on a massive sandstone block floating in a pool of mercury to dampen any possible vibration and to allow it to be rotated smoothly. The logic was impeccable. They would align one arm of the device with the direction of Earth's motion through the supposed ether. The light traveling down that arm would be like a swimmer going upstream and then downstream in a river. The light in the perpendicular arm would be like a swimmer going across the current and back. A careful calculation showed that the swimmer battling the current upstream and down would always take slightly longer to complete the round trip. So when the two beams of light were recombined, they should be slightly out of sync with one another. Their waves would no longer line up perfectly. This would create a specific predictable pattern of interference, a series of light and dark fringes. Then, by rotating the entire machine, the roles of the two beams would be swapped. The interference pattern should shift. That shift would be the definitive proof, the signature of the ether wind, the evidence of our planet's true voyage through the cosmos. They set up the experiment. They calibrated their mirrors with unprecedented precision. They held their breath and looked into the eyepiece, and they saw nothing. There was no shift. The interference pattern remained stubbornly, unnervingly fixed. They checked their calculations. They refined the instrument. They tried the experiment at different times of day, at different seasons of the year, hoping to catch the Earth at a different angle to the ether flow. Perhaps its motion around the sun was temporarily cancelling out the sun's motion through the galaxy. But no matter when or how they looked, the result was the same. A perfect, absolute, unwavering null. The ether wind was not there. The most important, failed experiment in the history of science had yielded a deafening silence. This wasn't just a disappointing result. It was a catastrophe for classical physics. It was a cosmic crime scene where the suspect had left no footprints. The implications were terrifying, and they pointed to one of two seemingly impossible conclusions. Either the Earth was somehow against all astronomical evidence stationary at the center of the universe, or something was profoundly fundamentally wrong with our understanding of light, of motion, of reality itself. The experiment seemed to be saying that the speed of light was constant, perfectly, bizarrely, impossibly constant for all observers. It didn't matter if you were racing toward a light source or away from it. The light would still pass you at the exact same speed. This idea was sheer madness. It defied all logic. If you are driving at 50 miles per hour and a car passes you doing 60, its speed relative to you is only 10. That simple, intuitive Newtonian addition of velocities. But light refused to play by these rules. Light seemed to break the game. The scientific community was in turmoil. They tried to invent theories to explain the null result. Perhaps the Earth dragged a little bit of the aether, along with it creating a calm pocket of space around our planet. Perhaps moving objects were physically compressed in the direction of their motion through the ether, an effect that would perfectly cancel out the expected time delay. These were desperate attempts to patch a sinking ship, to salvage the comfortable clockwork universe of absolute space and absolute time that had served them so well. They were building a wall of desperate complexity to hold back a simple but terrifying truth. The foundation itself was rotten. The old world was coming to an end. The stage was set for a revolution. A young patent clerk in Switzerland was about to take the strange, incoherent results from this failed experiment and accept them not as a paradox to be explained away, but as fundamental postulates about the nature of the cosmos. He was about to propose that if the speed of light is the one unbreakable constant, then everything else must be breakable, even space and time itself. In the quiet dawn of a new century, humanity believed it understood the world. The laws of the universe seemed all but solved, a grand cosmic clockwork, painstakingly revealed by giants like Galileo and Newton. Their physics was a masterpiece of common sense, a set of rules so elegant and predictable that we thought we had read the Creator's mind. There was just one small nagging problem, a ghost in the machine. A mystery that lurked in the heart of the most fundamental thing imaginable, a simple beam of light. And in a patent office in Bern, Switzerland, a young clerk, a man unremarkable to the world, was about to shatter that clockwork forever. His name was Albert Einstein, and he wasn't trying to break physics. He was just trying to understand why a beam of light refused to play by the rules. His journey would not lead to a minor correction in our theories. It would lead to a complete demolition and rebuilding of our concepts of reality. He would show us that the universe is far stranger, more beautiful, and more restrictive than we had ever dreamed. He would reveal a cosmic speed limit, one not made of matter or force, but woven into the very fabric of existence. To begin this journey, you must first accept a simple, intuitive truth. It's a principle so foundational that you experience it every day. Imagine you are in a vehicle, a starship perhaps, gliding through the void. The motion is perfectly smooth, utterly without vibration or acceleration. You release a ball from your hand. Where does it go? It falls straight down to your feet, just as it would on solid ground. You pour a drink and the liquid flows gracefully into the glass. You can perform any experiment from the simplest to the most complex, and the laws of physics will behave exactly as you expect them to. There is no experiment you can conduct inside your sealed cabin that can prove you are moving at all. Your velocity, whether it's 1,000 or 1,000,000 miles per hour, is utterly irrelevant to the physics unfolding within your world. This is the principle of relativity, an idea stretching back to Galileo. It simply states that the laws of nature are the same for all observers who are not speeding up or slowing down. It means there is no absolute privileged frame of reference in the cosmos. There is no true state of rest. You sitting there right now feel stationary, but you are on a planet spinning at 1,000 miles per hour, which is orbiting a star at 67,000 miles per hour, which is hurtling around the galaxy at 500,000 miles per hour. And yet your coffee does not fly from its cup. The universe does not care about your speed, only your change in speed. All constant velocity is relative. This was Einstein's first foundational stone, his first postulate. It was logical, it was tested, it was for all intents and purposes common sense. But it was his second postulate that would unleash a storm. It was an idea born from a failed experiment, a perplexing null result that had haunted physicists for decades. They had imagined space was filled with an invisible substance, the ether, the medium through which light waves were thought to ripple. If it existed, then Earth's motion through this ether should create a wind, a current that would alter the speed of light we measured, making it appear faster or slower depending on our direction of travel. Scientists built extraordinarily sensitive instruments to detect this ether wind, and they found nothing. Absolutely nothing. The speed of light was stubbornly, maddeningly, inexplicably constant. It was a cosmic crime scene with no culprit. While the greatest minds of the era tried to find elaborate ways to explain away this bizarre result to save the old theories, Einstein proposed something audacious, an act of supreme intellectual courage. He suggested we take the result at face value. What if the experiment wasn't a failure? What if it was revealing a new, profound, and deeply unsettling law of nature? What if the speed of light in a vacuum is the same for every single observer, regardless of their own motion or motion of the light source? This was his second postulate, and it tears common sense to shreds. Consider this. You are on a cosmic highway in a spaceship, traveling at a blistering pace. Another ship flashes past you, moving in the same direction but even faster, at 90% of the speed of light. From its cockpit it fires a laser beam forward. Now our intuition, our entire experience of the world, tells us we should add these velocities together. The speed of the spaceship plus the speed of the light it emits. But the universe says no. If you measure the speed of that laser beam as it races away, you will not find it moving at 190% of light speed. You won't even find it moving at 101%. You will measure it to be moving at exactly the speed of light. No more, no less. Now imagine a ship flying towards you at that same incredible velocity. It shines its headlights in your direction. The closing speed should be immense, a colossal addition of velocities. But again, the universe forbids it. You will measure that incoming light and find it is traveling towards you at precisely the speed of light. It is an absolute, an unbreakable, cosmic constant. This one fact, this bizarre refusal of light to behave like anything else, is the key that unlocks the entire structure of the universe. Because if the speed of light must remain the same for everyone, then something else, something we thought was absolute, must give way. That something is space, and most profoundly time itself. Einstein realized that if these two postulates were true, If physics is the same for all, and the speed of light is constant for all, then space and time could no longer be the rigid, unyielding backdrop we had always imagined. They must be flexible, malleable, personal. They must warp and stretch and compress in order to conspire in a grand cosmic collusion to protect the constancy of light. To see how this works, we must enter Einstein's laboratory, his own mind. Join him in a thought experiment, a Gedanken experiment. Picture a clock, but not just any clock. This is the simplest, most perfect clock imaginable. It consists of two mirrors facing each other. A single particle of light, a photon, bounces between them. Every time the photon strikes the bottom mirror, the clock registers one tick. The distance between the mirrors is fixed, and the speed of the photon is constant, so the ticks of this light clock are perfectly metronomically regular. Tick, tock, tick, tock. Now let's place this clock on a transparent train, a spaceship, and watch it glide past us at a constant, very high velocity. From the perspective of a person riding along with the clock, nothing has changed. The photon continues its simple journey straight up and straight down. Tick, tock. The laws of physics are the same for them as the first postulate demands. But what do we standing on the station platform observe? As the clock moves, we see the photon travel on a different path. It leaves the bottom mirror, but by the time it reaches the top mirror has moved forward. To catch up, the photon must travel along a diagonal line. Then it must travel down another diagonal line to strike the bottom mirror, which has also moved forward in the meantime. From our stationary vantage point, the light particle is tracing a zigzag pattern, a V shape for every single tick-tock. Here is the moment where reality breaks from intuition. The path the photon now travels, this diagonal path, is undeniably longer than the simple up and down path seen by the person on the train. This is not an illusion, it is a geometric fact. And yet Einstein's second postulate is absolute. The speed of that light particle must be exactly the same for us as it is for the observer moving with the clock. But if the light is traveling a longer distance and its speed cannot change, how is this possible? There is only one conceivable answer, one earth-shattering conclusion. Time itself must be passing more slowly for the moving clock. The tick must take longer to complete from our point of view. If the light travels farther but at the same speed, each journey must last longer. The flow of moments, the very progression of duration for that clock, must dilate, must stretch to preserve the cosmic speed limit. This is not a mechanical failure of the clock. It is not an illusion. It is a fundamental property of the universe. Time flows at different rates for different observers. The faster you move through space, the slower you move through time. Your personal clock, the rhythm of your own existence, slows down relative to the universe you are flying through. For centuries, time was seen as a universal river flowing at the same rate for everyone, a grand cosmic metronome that ticked in unison for all beings everywhere. Einstein revealed that this was a profound misunderstanding. There is no single river of time. There are countless streams, billions upon billions of them, one for every object, every person, every planet in the cosmos, and the rate of flow for each stream is determined by its motion. This isn't theoretical speculation. We live with this reality every single day. The global positioning satellites that orbit our planet are moving at thousands of miles per hour relative to us on the surface. Their onboard atomic clocks tick just a tiny fraction slower than clocks on the ground by a few microseconds each day. It's a minuscule amount, but if engineers didn't account for this time dilation, GPS systems would become inaccurate by miles within a single day. The strange elastic time of Einstein is built into the technology in your pocket. We see it in the world of particle physics, in colossal accelerators that smash atoms together at near the speed of light. Many of the subatomic particles created in these collisions are incredibly unstable, existing for only a few trillionths of a second before they decay. Yet, because they are traveling so astonishingly fast, their internal clocks are slowed down dramatically from our perspective. We can watch them survive for far, far longer than their natural lifespan should allow. They are, in essence, tiny time travelers propelled into their own brief future by their incredible velocity. But the consequences of this cosmic conspiracy do not end with time. If time is relative, then so is the very concept of now. Let's return to our high-speed train. Imagine it is immensely long. A person is standing precisely in the middle of a carriage. At the exact same moment, two bolts of lightning strike the train, one at the very front and one at the very back. For the person on the train standing in the middle, the light from both strikes travels an equal distance to reach their eyes. The flashes arrive at the same instant. They will declare correctly from their perspective that the two strikes were simultaneous. They happened at the same time. But what about us watching from the platform as the train speeds past? As the two flashes of light travel from the ends of the train towards the center, the person in the middle of the train is moving towards the light from the front strike and away from the light from the rear strike. Therefore, the light from the front of the train has a shorter distance to travel to reach them. It will arrive at their eyes first. The light from the back of the train chasing a moving target arrives a moment later. From our perspective on the platform, the lightning did not strike simultaneously. The front of the train was struck first, then the back. Who is right? Einstein's profound answer is, both of you are. Simultaneity is relative. There is no universal now that we all share. The idea of a single instantaneous moment across the entire cosmos is an illusion. My now is different from your now if we are in motion relative to each other. The very order of events can be different for different observers. This shattering of a universal now leads directly to the next bizarre consequence. If we cannot agree on whether two things happen at the same time, then we can no longer agree on the length of an object. To measure the length of something like our moving train, you have to mark the position of its front and back ends at the exact same instant. But we have just proven that the exact same instant is a relative concept. An observer on the train using their own synchronized clocks will measure its proper length, its rest length. But for us on the platform, our definition of now is different. We will see the train as being shorter in its direction of motion. Space itself contracts. Just as the universe slows down time to protect the speed of light, it also squeezes space. Time dilation and length contraction are not two separate phenomena. They are two sides of the same coin, two inseparable strategies employed by reality to ensure that no matter what you do, a beam of light will always fly past you at 299792458 meters per second. As an object approaches the speed of light, these effects become extreme. From our perspective, its clock would slow to a near standstill. A single second for it could be 1,000 years for us. And its length in the direction of motion would shrink towards nothing. The universe itself would appear to flatten into a two-dimensional panorama from the perspective of a photon. But there is a final and perhaps most crucial piece to this puzzle. The ultimate barrier that makes the speed of light an absolute summit, a peak that matter can never ever reach. It lies in Einstein's most famous and most misunderstood equation, E gleich mc Quadrat. We usually associate this with the terrifying power of nuclear weapons, the conversion of a tiny amount of mass into a vast amount of energy. But the equation works both ways. It tells us that energy and mass are two facets of the same fundamental thing. Mass is a fantastically concentrated form of energy, and energy in turn has mass. It has inertia. It resists being pushed. Now think about what it takes to make something go faster. You must put energy into it. You apply a force which transfers kinetic energy, the energy of motion, to the object. At low everyday speeds, this is straightforward. More energy equals more speed in a simple linear relationship. But as you start approaching the cosmic speed limit, something strange happens. The energy you are pumping into your spaceship starts to manifest differently. Your engines are blazing, consuming gargantuan amounts of fuel, pouring unimaginable quantities of energy into your motion. But your gains in velocity become smaller, and smaller, and smaller still. The ship fights you back. It becomes harder and harder to accelerate. Why? Because according to E equals mc squared, the kinetic energy you are adding to the ship is also adding to its mass. The faster you go, the heavier you become. Not in the sense of feeling a stronger gravitational pull, but in the sense of inertia. Your resistance to any further change in motion grows. It's a cosmic law of diminishing returns. As you approach 99% of the speed of light, your mass has already increased by a factor of 7. You now require 7 times the energy to achieve the same small increase in speed that you did when you started. At 99.9%, your mass is 22 times greater. At 99.999%, it's over 200 times greater. As you get tantalizingly, infinitesimally close to the speed of light, your relativistic mass approaches infinity. The ship's resistance to acceleration becomes infinite. To nudge it over that final impossible threshold to make it cross the finish line and actually reach the speed of light, you would need to supply it with an infinite amount of energy. More energy than exists in the entire observable universe. The cosmos has erected an infinite wall of energy at its ultimate frontier. The speed of light is not merely a speed. It is a fundamental boundary, a true asymptote carved into the geometry of reality. Massless things like photons can travel at this speed because they have no rest mass to begin with. They are born at light speed and will die at light speed. But for anything made of matter, you, me, our spaceships, our dreams, it is a destination we can approach but never ever reach. Einstein, the humble patent clerk, had done more than just solve a puzzle about light. He had completely overthrown our notions of the stage upon which our lives unfold. He showed us that space was not a fixed, empty void, and that time was not a universal ticking clock. He fused them together into a single dynamic, four-dimensional entity space-time, a unified fabric that can bend, stretch, and twist all to uphold one single sovereign law. The speed of light is not just a limit, it is the law. It is the very definition of causality, the rate at which effects can follow their causes. It is the ultimate speed of information, the pace at which one part of the universe can communicate with another. To break this law would be to shatter the logical structure of reality itself, and so the universe protects it at all costs, sacrificing the constancy of time and space to preserve this one perfect constant. This is the world as it truly is. Strange, beautiful, and bound by a law we can never hope to break. We have chased a phantom across the cosmos. We have imagined engines capable of bending space, of drinking the energy of stars, of defying gravity itself. But we have always been operating under a comforting illusion. The illusion that the universe is a passive stage, an empty arena waiting for our technological prowess to conquer it. That all we need is a more powerful engine, a bigger rocket. That speed is merely a matter of applying enough force for enough time. That illusion ends now, because the final barrier to light speed is not an engineering problem. It is not a challenge of fuel or materials or distance. It is something far more profound. The final barrier is the universe itself. It is a law woven into the fabric of existence, a cosmic commandment that states in no uncertain terms, "Thou shalt not." To understand why we must abandon the comfortable world we know, for centuries our understanding of motion was beautifully simple. It was the world of Isaac Newton, a universe of perfect clockwork. Push an object and it accelerates. Push it harder and it accelerates more. If you could keep pushing, it would keep going faster and faster indefinitely. There was no inherent speed limit, no cosmic governor. The only constraints were friction, air resistance, and fuel. In the sterile vacuum of space, with a perfect engine, any speed seemed possible. It was a universe of linear, predictable, and reassuring rules. A universe that, as it turns out, is only a local approximation, a gentle fiction the cosmos tells us here in the slow lane. Because as we venture out to the frontiers of velocity, we discover something unsettling. The universe is not a passive stage. It actively participates in the act of motion. It pushes back. It changes the rules of the game right when we are about to win. The closer we get to that ultimate prize, the speed of light, the more the universe itself seems to conspire against us. It alters the very definition of the thing we are trying to move. It transforms our vessel, our starship, into its own enemy. To see how we must look not at the engine but at the essence of matter itself, we must look at mass. In our everyday lives, mass is a constant. A kilogram of sugar is a kilogram of sugar. It does not matter if it is sitting on your kitchen counter, or in a car, or on a jet plane. Its mass, its fundamental amount of stuff, feels absolute. This is what physicists call rest mass. It is the intrinsic, unchangeable property of an object at rest. It is your anchor to the universe, your measure of inertia. For the longest time, we believed this was the only kind of mass. But a young patent clerk in Bern, Switzerland, dreaming of riding on a beam of light, would shatter that certainty. Albert Einstein, with his theory of special relativity, revealed that the universe is far stranger than we ever imagined. He showed us that time can slow down and space can contract. And he unveiled the most counterintuitive truth of all. He showed us that mass is not constant. It is dynamic. It is fluid. It is relative. As you begin to move, as your starship ignites its engines and leaves the slow, comfortable world behind, something extraordinary begins to happen. From the perspective of the universe you are traveling through, your mass begins to increase. It is a concept so alien it feels like a violation. How can an object become heavier just by moving? Where does this new mass come from? It comes from the motion itself. Your energy of movement, your kinetic energy, begins to manifest itself as additional mass. Imagine you are a swimmer cutting through a tranquil pool. The water provides a certain resistance. Now imagine that the faster you swim, the thicker the water becomes. At first the change is imperceptible, but as you pour more and more energy into your stroke, the water transforms from liquid to syrup, then to tar. Soon you are fighting with all your might just to move an inch. Your heroic effort is being used not just to gain speed, but to fight against a medium that your own motion makes hostile. This is what the universe does. Space itself becomes that thickening medium. Let's put some numbers to this cosmic drag. Imagine your starship, a sleek vessel with a rest mass of 1,000 tons, a solid, tangible number. You fire the engines. You accelerate. At 10% of the speed of light, a blistering 67 million miles per hour, your mass has increased by only 0.5%, just 5 extra tons. The universe is barely resisting. Your engine hardly notices the difference. You push harder, pouring unimaginable power into the drive. You reach 50% of light speed, 335 million miles per hour. Now the scales tell a different story. Your ship from the outside now behaves as if it has a mass of over 1,150 tons. An extra 150 tons of mass have appeared, forged from the pure energy of your acceleration. You are carrying the ghost of your own motion. But this is only the beginning of the tyranny. The relationship is not linear. It is a runaway curve, an exponential explosion that dooms the entire enterprise. Let's push the engine to its limits. 90% of the speed of light, an incredible velocity on the very cusp of our ultimate goal. Your 1,000-ton vessel now fights you with the inertia of more than 2,290 tons. Its mass has more than doubled. Every thruster burn, every unit of energy you expend is now twice as difficult as it was when you were at rest. You are fighting a shadow that grows with every forward step. Now for the final desperate surge. You channel the power of a small star into your drive systems. You are clawing your way through the final percentages. At 99% of light speed, your ship's mass swells. It now registers at over 7,000 tons. At 99.9%, it escalates to 22,000 tons. The thickening water has become a wall of solid diamond. Your ship is no longer a sleek vessel. It has become a monster of its own, making a monument to inertia bloated by the very speed you crave. And this is not just a mathematical abstraction, it is physically real. If your ship were to collide with a stationary object at this speed, it would impact with the momentum of that colossal mass. The laws of physics perceive and treat your ship as being that heavy. It has more inertia. It resists changes in direction more stubbornly. And crucially, it resists acceleration more fiercely. This is the heart of the problem. This is the engine's ultimate nightmare. You are in the command chair of this vessel hurtling through the void. Your mission to achieve the impossible. Your engine is a miracle of future science, a perfect converter of fuel to thrust. But this perfect engine is now yoked to an impossible task. Newton's second law of motion is simple. Force equals mass times acceleration. You want to keep accelerating to gain that next increment of speed. But the mass in that equation is no longer a fixed number. It is a variable that is exploding toward infinity. To get the same amount of acceleration as you did at the start of your journey, you now need to generate thousands of times more force, and for the next increment, after that tens of thousands more. This is where we must confront the true currency of the cosmos: energy. The most famous equation in all of science now enters the scene not as a key, but as a lock. E equals mc squared. Energy equals mass times the speed of light squared. We usually think of this as the recipe for unlocking the power of the atom. A tiny amount of mass can be converted into a tremendous amount of energy. But the equation is a two-way street. It is a cosmic ledger that must always be balanced. Energy can be converted into mass, just as mass can be converted into energy. And that is precisely what is happening to your ship. The colossal amounts of energy you are pumping into your vessel to increase its velocity are not all going into speed. A vast portion of that energy is being diverted by the universe. It is being transformed according to Einstein's law into mass. You are pouring fuel into the engine, and that fuel is literally making your spaceship heavier. You are not just pushing a ship anymore. You are attempting to push the accumulated energy of your entire journey. Your past efforts are actively working against your future goals. It is a law of diminishing returns on a cosmic soul-crushing scale. Let's imagine the fuel requirements. Let's grant you the most efficient fuel source theoretically possible: matter-antimatter annihilation, the complete conversion of mass to energy, a perfect fuel. To accelerate your 1,000-ton ship to 50% of light speed, you would need to annihilate about 150 tons of antimatter. A staggering amount, but let's assume you have it. Now, to get from that 50% mark up to 90% light speed, a smaller increase in velocity, you would expect to use less fuel. But the tyranny of relativistic mass has taken hold. For this next leg of the journey, you would need to burn through an additional 1,140 tons of antimatter, nearly 8 times the energy for a smaller gain in speed. The cost has become exorbitant, but we press on. The goal is in sight. We want to go from 90% to 99.9%, a sliver of a gain, a tiny fraction of the total velocity. How much fuel does this last push cost? The answer is horrifying. It would require the annihilation of more than 19,000 tons of antimatter, 19 times the mass of your actual ship. you would need a fuel tank that massively dwarfs the vessel it is supposed to power. And here the trap snaps shut, because that fuel has mass. All those thousands of tons of antimatter you must carry with you from the start also have to be accelerated. So now you must accelerate your ship and the fuel needed for the end of the journey, which requires even more fuel, which in turn has more mass and requires still more fuel to accelerate. It is a recursive, vicious feedback loop that spirals instantly to impossibility. It's like trying to climb out of a hole by standing on your own shoulders. The very act of carrying your solution makes the problem infinitely worse. The universe has presented us with a riddle that has no answer, a race that is rigged from the start. We have arrived at the final moment of the chase. The last infinitesimal gap between our ship and the speed of light. 99.999%. We are pacing a photon. We can almost reach out and touch it. The ship's drive is glowing with the fury of a supernova. It is consuming more energy per second than all of human civilization has produced. The mass of our vessel has ballooned to astronomical proportions. It is now heavier than a mountain, heavier than a small moon. A phantom moon made of pure solidified motion. It fights us with an inertia that is almost absolute, and we are still not there. What happens in that final impossible leap? What is the price for that last fraction of a percentage point? The mathematics of relativity, which have been proven correct in countless experiments for over a century, are unequivocal. They do not bend, they do not compromise. They deliver a final absolute verdict. As your velocity v approaches the speed of light, crew, the equation that governs your mass increase, contains a deadly term. It divides by the square root of 1 minus v squared over c squared. As v gets closer and closer to c, that denominator gets closer and closer to 0, and any number divided by 0 is infinity. At the exact forbidden moment your ship would touch the speed of light, its mass would become infinite. And to accelerate an infinite mass, even by the smallest amount, you would require an infinite amount of energy. Infinity. Not just more energy than a star, not just more energy than a galaxy, but more energy than exists in the entire observable universe. It is the ultimate price tag for a product that can never be delivered. This is the end of the line. The chase is over. It is not a technological barrier we have hit. It is a logical one. It is the architecture of reality itself. The universe does not have infinite energy to give. Therefore, you, I, this ship, anything made of matter, anything with even a single atom of rest mass can never ever reach the speed of light. It is the most democratic law in existence. It applies to the smallest bacterium and the largest galaxy. Everything that is something is bound by this rule. So why can light do it? Why can a photon, the very particle we are chasing, travel at the speed it is forbidden to us? Because a photon is in a very real sense nothing. It has zero rest mass. It has no anchor to the slow world. It cannot be at rest. For a photon, traveling at the speed of light is not a goal to be achieved. It is its only possible state of existence. It is born at that speed, it lives at that speed, and it dies at that speed. It knows no other way. For matter, it is the one speed that is prohibited. For light, it is the one speed that is mandatory. The universe is built on this beautiful, stark duality. This cosmic speed limit, this infinite wall, might feel like a prison, a cage that confines us to our galactic neighborhood. A final insurmountable frustration, but that is a failure of perspective. This law is not a cosmic cruelty. It is a pillar of creation. It is a guarantee of sanity. It is what makes the universe comprehensible. It enforces causality. It ensures that cause always precedes effect. It prevents the paradoxes that would unravel time itself. The impossibility of reaching light speed isn't a limitation, It is a profound and elegant truth. It is the signature of a cosmos governed by unshakable reason, and it is the fundamental reason why we will always be the chasers, never the catch. We have spent our journey confronting a wall, a barrier of pure light woven into the fabric of reality itself. We have treated it as a cosmic speed limit, a finish line we can never cross. But what if we have been asking the wrong question all along? What if this barrier is not a limitation, but a form of protection? What if the speed of light is the one law holding the universe together? To understand why, we must dare to imagine the impossible. We must perform an act of cosmic rebellion, a thought experiment so profound it threatens the very logic of our existence. Let us pretend for a moment that the barrier can be broken, that a ship or a particle or a signal could tear through space-time at a velocity faster than the universe permits. What awaits us in that forbidden territory beyond the light? It is not a realm of infinite speed or glorious new frontiers. It is a place where the rules that govern reality unravel completely. A place where yesterday is no longer gone and tomorrow has already happened. A place where the story of the cosmos ceases to make any sense. Physics has a name for these phantoms that haunt our equations. They are called tachyons. These are not just particles that have been accelerated past the light barrier. They are entities born into a state of superluminal existence. For them, the speed of light is not a ceiling but a floor. A tachyon can never travel at the speed of light or slower. It is forever trapped in the realm of the impossible, living a life in reverse. Imagine a particle whose energy works backwards. For every piece of matter you have ever encountered, from a speck of dust to a galaxy, adding energy makes it move faster. This is the intuitive engine of our universe. But a tachyon would defy this fundamental principle. To make a tachyon accelerate, to make it go even faster, you would need to take energy away from it. As its velocity climbed towards infinity, its energy would drop towards zero. Conversely, to slow a tachyon down to bring it closer to the speed of light, you would need to pump it with a truly staggering amount of energy. Slowing it to the precise speed of light would require an infinite quantity. This cosmic inversion is a hint, a mathematical warning sign that we are treading on treacherous ground. These hypothetical particles are like echoes from a mirror universe, one where all the familiar laws of motion are reflected and distorted. For decades, physicists have searched for them, seeking a telltale signature, a particle that appears out of nowhere, seemingly violating conservation laws, only to vanish an instant later. Some experiments looked for exotic radiation, a kind of shock wave in space-time that a superluminal particle might create as it tears through the vacuum. This Cherenkov radiation in a vacuum would be an unambiguous signal, the sonic boom of something breaking the ultimate cosmic law. But every search has returned empty. The cosmos remains silent. Not a single verifiable tachyon has ever been found. They remain ghosts in the machine of theoretical physics. A fascinating but perhaps purely mathematical what-if, yet their theoretical existence forces us to confront a terrifying possibility. It provides the key to unlocking the deepest reason why the light-speed barrier must be absolute. The existence of any particle, any signal, any vessel that can move faster than light would not just break a rule of physics, it would shatter the very notion of time itself. It would destroy the most sacred principle of our reality, the unyielding, unbreakable chain of cause and effect. Causality. It is the most fundamental narrative structure of the universe. A glass falls and then it shatters. A star collapses and then a supernova ignites. An action is performed and then a consequence unfolds. A precedes B. The cause always comes before the effect. This is not merely an observation. It is the bedrock of logic, of history, of our ability to comprehend the world. Without it, reality dissolves into an incoherent fever dream. And this is precisely what a faster-than-light world would create. to understand how we must look to Einstein's most startling revelation. He showed us that time is not a universal clock ticking at the same rate for everyone. Time is relative. It stretches and it shrinks depending on your motion. Crucially, he also revealed the relativity of simultaneity. This means two different observers moving at different speeds can disagree on the precise order in which two separate events occur. For you standing still, two lightning bolts might strike at the exact same moment. But for someone flying past in a high-speed ship, one bolt will appear to strike before the other. As long as nothing travels faster than light, this disagreement is harmless. It is a quirk of perspective. The order of events that are causally connected remains untouchable. No one, no matter their speed, will ever see the glass reassemble itself and leap back onto the table before it fell. The light from the falling glass simply doesn't have time to reach an observer in a way that could invert the sequence of cause and consequence. The speed of light acts as the ultimate cosmic enforcer, ensuring the story of the universe is always told in the right order. But now let us introduce our outlaw. Imagine we have a ship, the Paradox, capable of superluminal travel. We set up an experiment across the vastness of interstellar space. On Earth, a control station is ready to send a message. 4 light-years away near Proxima Centauri, our ship waits. At precisely noon, Mission Control on Earth sends a simple message: engage. This signal, traveling at the speed of light, will take 4 years to arrive. It will reach the Paradox ship in the year 2028. This is Event A, the cause. The Paradox receiving the message is Event B, the effect. Simple. But the Paradox has a faster-than-light drive. Let's say it can travel at twice the speed of light. Upon receiving the message in 2028, it immediately turns around and flies back to Earth. Traveling at twice light speed, the 4 light-year journey takes only 2 years. The Paradox ship arrives back at Earth in the year 2030. So far, everything seems logical. Strange, but logical. But now we must account for the relativity of simultaneity. Let us view this entire sequence from the perspective of another observer. Imagine a second ship, the Witness, flying by the solar system at a high speed at a significant fraction of the speed of light. From its unique frame of reference, time itself is distorted. The sequence of events we just described looks profoundly different. According to the mathematics of relativity, from the Witness's point of view, the Paradox ship's return journey is so compressed in time that its arrival back on Earth doesn't just happen quickly. It is calculated to happen before it even left Proxima Centauri. Even more disturbing, with the right velocity and trajectory, the Witness would see the Paradox ship arrive back at Earth in the year 2025. Think about what this means. Earth sends a signal in 2024. The Paradox ship arrives back on Earth in 2025, a full 3 years before it is due to receive the signal that sent it on its journey in the first place. This isn't a trick of perception or an optical illusion. In the Witness's valid, legitimate frame of reference, the effect has occurred before the cause. The ship has returned from a mission it has not yet been ordered to begin. It has brought back information from a future that is yet to happen. We have just invented a time machine, and not just any time machine. We have created a weapon that targets the logical integrity of the cosmos. We have built a tachyon telephone, a device for sending messages into our own past. And with it, we can orchestrate the end of reason itself. The ability to transmit information backwards through time opens a Pandora's box of paradoxes from which reality could never recover. These are not scientific puzzles to be solved. They are fundamental contradictions, logical impossibilities that would tear the fabric of space-time into shreds. The most famous of these is the grandfather paradox. It is a story of cosmic self-destruction. Using our superluminal transmitter, you send a message to the past. A simple message sent to a specific person 20 years ago, your own grandfather. The message contains a warning, a piece of information designed to prevent him from ever meeting your grandmother. Perhaps you warn him of a danger at the place where they were fated to meet, urging him to stay home that day. The message arrives in the past. Your grandfather heeds the warning. He never meets your grandmother. As a consequence, your mother or father is never born, and therefore you are never born. But if you were never born, you could never have grown up to become a scientist. You could never have built the faster-than-light transmitter, and you could never have sent the warning message back in time. So the message is never sent. Your grandfather, unwarned, proceeds to his fateful meeting. He meets your grandmother. They fall in love. Your parent is born, and eventually you are born. You grow up, become a scientist, and haunted by some memory or desire, you build the transmitter and send the message back. The loop closes, and it is a loop of pure illogic. Both outcomes, your existence and your non-existence, depend on the other in a way that is mutually exclusive. The universe is asked to accommodate two contradictory realities at once. It is a question with no possible answer. A cosmic 404 error. The timeline fractures. Did the event happen or not? The very concept of a consistent history evaporates. The universe becomes a story that constantly writes and erases its own beginning. But this is not the only path to incoherence. There is another, perhaps more insidious form of paradox, the bootstrap paradox or the causal loop. This is not a story of self-destruction but of uncreation. An object or a piece of information is trapped in a loop of time with no discernible origin. Imagine an aging engineer obsessed with building a time machine. One day, a mysterious younger woman visits him. She gives him a notebook filled with complex diagrams and equations, the complete blueprints for a working time machine. The engineer spends the next 30 years of his life building the device. He succeeds. As his final act, he gives the now worn notebook to his young assistant, the same woman who visited him decades ago, and sends her back in time to give the plans to his younger self. The loop is complete. The time machine exists. But ask yourself a simple question: who designed it? The old man only built it because he got the plans from the young woman. The young woman only had the plans because she got them from the old man. The information, the genius of the design, came from nowhere. It simply is. It has no point of creation, no author, no moment of invention. It is a ghost, an idea that created itself, bootstrapped into existence. Now, apply this to the cosmos. A superluminal ship could carry a star chart of an undiscovered galaxy back in time and give it to an astronomer. The astronomer then uses the chart to discover the galaxy. Where did the knowledge of that galaxy's layout originate? The universe would become filled with uncaused information, with effects that have no preceding cause. The entire history of scientific discovery, of life's evolution, of the formation of galaxies, could become a set of closed loops, an endless library of books that were never written by anyone. This is a universe devoid of meaning, without a past that leads to a present. It is a place where history has no anchor. Every event could be its own cause. The arrow of time, that steadfast progression from yesterday to tomorrow, would shatter into a million confusing, contradictory pieces. A universe with faster-than-light travel is a universe that cannot sustain a coherent narrative of its own existence. And so we arrive back at the wall of light. We see it now, not as a prison fence, but as a sea wall holding back an ocean of pure logical chaos. The speed of light is not a cosmic tyrant forbidding us from the stars. It is the great protector of causality. It is the ultimate law that ensures the universe makes sense. This is its profound purpose. It guarantees that effects follow their causes in an unbroken chain stretching all the way back to the first moment of the Big Bang. It ensures that the past is fixed, the present is happening, and the future is yet to be written. The barrier is not a physical obstacle in the way that a mountain is an obstacle. It is a fundamental pillar of the logical structure of reality. To break it would be like removing the concept of before and after from our language. The story we could tell would descend into meaningless babble. So we will never reach the speed of light. We will never build a tachyon telephone or a ship that can outrun its own past. And that is perhaps the greatest blessing the universe has given us. We are creatures of time and consequence. Our lives, our memories, our hopes are all built upon a stable timeline. We exist because one moment reliably follows the next. The speed of light is the guarantor of this sacred order. It is the silent, unwavering sentinel that allows a story, our story, to be told at all. The ultimate speed limit is not a boundary on our ambition. It is the very foundation of our sanity. The universe has declared a law, a final, unbreakable speed limit, a cosmic decree etched into the very fabric of existence. We have stared at this boundary, this golden cage of light speed, and felt the immense sorrowful weight of its finality. But humanity's spirit is not one of passive acceptance. It is a restless, defiant force that when faced with a wall does not just ask how to climb it, it asks if the wall itself is real. What if the barrier is not a limitation on our velocity, but merely a limitation on our thinking? What if the goal was never to outrun the light, but to rewrite the journey? The quest for the stars has forced us to evolve our dreams to move beyond the brute force of engines and acceleration and into a realm of physics so strange, so utterly profound, it borders on the magical. This is the story of cheating the cosmos at its own game. Not by breaking the law, but by finding its loopholes. By manipulating the very stage on which the drama unfolds, space-time itself. Our first glimpse of a cosmic shortcut, a divine backdoor, came not from engineering, but from the mind of Einstein. Hidden within the labyrinthine mathematics of general relativity, he and his colleague Nathan Rosen found something impossible. A ghost in the machine of the universe. A theoretical structure that connected two distant points in space-time, not with a line, but with a bridge, a tunnel, a wrinkle in the cosmic fabric. We call them wormholes, or more formally Einstein-Rosen bridges. Imagine you are an ant on a vast sheet of paper. To travel from one side to the other is a long and arduous trek. You are bound by the rules of that two-dimensional universe. But what if a higher intelligence could bend that paper, folding it until the start and end points nearly touched? Then what if it could puncture the paper at both points, creating a tiny tunnel that connects them directly? For the ant, it would be a miracle, a journey of 1,000 steps reduced to just one. It hasn't moved faster. It hasn't broken its own speed limit. The universe itself simply became smaller for a moment. This is the sublime promise of a wormhole. Not a faster ship, but a shorter sea. A pathway from our solar system to the Andromeda galaxy, not in 2.5 million years, but in an instant. A gateway to worlds so distant their light has barely begun its journey to us. It is the ultimate dream of exploration. A way to render the cosmos in all its terrifying immensity suddenly intimate. The theory is beautiful, it is elegant, and in its purest form, it is catastrophically lethal. The original Einstein-Rosen bridge is not a welcoming gateway, it is a cosmic trap of unparalleled ferocity. The throat of this theoretical wormhole is an event horizon, a one-way membrane from which nothing, not even light, can return. Worse still, the bridge is fantastically unstable. It opens and closes with unimaginable speed in a time frame, so infinitesimally small that not even a single photon could pass through. To attempt a crossing would be to pilot your ship into a door that slams shut with the force of a collapsing universe. You wouldn't be transported. You would be annihilated, crushed into a singularity, a dead end. Another cosmic law reasserting its dominance. But the story does not end there. Physics is a conversation across generations, a relentless search for a what-if. In the latter half of the 20th century, physicists like Kip Thorne revisited this cosmic puzzle with a new question. What if you could prop the door open? What would it take to stabilize a wormhole to transform it from an ephemeral, lethal trap into a stable, traversable conduit through space-time? The answer they found is what propels this concept from the realm of mathematics into profound theoretical physics. And it is where the true weirdness begins. To hold a tunnel through space-time open against the crushing pressure of its own geometry, you need something extraordinary. You need a substance that defies one of the most fundamental properties of the universe we know. You need matter with anti-gravity. Normal matter, the kind that makes up you, me, the planets and the stars, has positive mass and positive energy. It pulls things together. It causes space-time to curve inward, to dimple, to create gravity wells. To counteract this, to pry space-time open and hold it there, you require something with negative energy density, something that would warp space-time outwards, a substance that if you held it in your hand might possess negative mass. If you were to push it, it would accelerate towards you. It would fall up, not down. We call this exotic matter. It is not merely rare or undiscovered. It is a form of substance whose very existence would rewrite physics. It's a cosmic scaffold, an anti-gravitational jack needed to support the architecture of your shortcut. The energy requirements are staggering. You would need to gather a colossal amount of this material, this hypothetical anti-gravity stuff, and carefully line the throat of the wormhole with it. This negative energy would push outward against the universe's tendency to crush the tunnel, creating a stable, open passage, a gateway a ship and perhaps a human could survive. Where would we find such a thing? Nowhere we have ever looked. Quantum mechanics does permit fleeting microscopic moments of negative energy in the vacuum of space, the so-called Casimir effect. But these are localized, transient fluctuations, not a substance one can mine or manufacture in bulk. Could a hyper-advanced civilization, masters of cosmic engineering, learn to harvest this quantum foam to weave these fleeting negative energy moments into a stable material? We have absolutely no idea. We are like ancient mariners trying to comprehend a nuclear submarine. The principles feel like a violation of the natural order. And even if we could somehow conjure this exotic matter, even if we could build our bridge across the cosmos, we would face a new and perhaps more terrifying problem. A problem not of physics but of causality. A wormhole doesn't just connect 2 points in space. It connects 2 points in space-time. And by moving the ends of the wormhole at relativistic speeds, you could create a bridge not just to another galaxy, but to another time. You could, in theory, construct a wormhole whose entrance is in your present but whose exit opens into Earth's past. You could step through a doorway and arrive before you left. Suddenly, you are no longer just an explorer. You are a potential paradox. The spectre of the grandfather paradox of altering the past, of creating a timeline that prevents your own existence, emerges from the mathematics. Does the universe have laws to prevent this? Some physicists propose a chronology protection conjecture, a yet undiscovered principle of physics that forbids time travel, perhaps by causing a feedback loop of energy that would destroy any wormhole before it could be used to violate causality. The universe, it seems, may have its own immune system to protect the integrity of its timeline. The wormhole, once a dream of infinite possibility, becomes a profound philosophical minefield, a gateway that challenges our very understanding of cause and effect. So the cosmic shortcut remains a tantalizing but seemingly unreachable prize. It demands a substance we cannot prove exists to solve a stability problem we cannot overcome, and creates paradoxes that threaten the fabric of reality. Faced with this impasse, another audacious idea was born. an idea that also seeks to manipulate space-time, but in a radically different way. It shifts our thinking from topology, the art of the tunnel, to geometry, the art of the wave. What if instead of punching a hole through space, you could simply ask space to bring your destination to you? This is the theory of the warp drive. First proposed in a mathematically rigorous form by physicist Miguel Alcubierre, the concept is as elegant as it is mind-bending. Imagine your spacecraft is encased in a bubble of flat, undisturbed space-time. It is your own personal portable island of normality. Inside this bubble, you are not moving at all. You are weightless at rest. You violate no physical laws. You feel no crushing acceleration. The magic happens outside the bubble. The warp drive, powered by unimaginable energies, would manipulate space-time around your vessel. In front of the bubble, it would cause space-time to contract, pulling your destination closer. Behind the bubble, it would cause space-time to expand, pushing your starting point further away. Your ship isn't a projectile moving through space. The ship is a passenger, and the space itself is the conveyance. It's like being a surfer on a wave. The surfer is not moving faster than the water molecules in the wave can oscillate. Instead, the surfer is being carried by the wave itself, a moving distortion of the medium. Here, your ship is the surfer, and the wave is a distortion of space-time. The bubble of space-time containing your ship can be propelled forward at a velocity that is, from an outsider's perspective, many times the speed of light. Yet, locally within your bubble, light still travels past you at exactly the speed of light. The universal speed limit is never broken. It is simply circumvented. You are in a ship inside a bottle while the ocean itself moves. The law is upheld, yet the cosmos is crossed. It is perhaps the most beautiful cheat ever devised. A way to achieve faster than light travel without ever actually moving faster than light. It avoids the infinite energy, infinite mass, and time dilation problems of conventional acceleration. It is a purely general relativistic solution. It works perfectly on paper. And like the wormhole, it comes with a list of requirements, so impossibly demanding they make the dream seem like a feverish hallucination. The first and most formidable obstacle is once again energy. And not just any energy. To make the Alcubierre drive work, to create the necessary space-time curvature, you need that same phantom substance from the wormhole conundrum. You need exotic matter. You require a region of negative energy density to create the expansion of space-time behind your ship. The initial calculations by Alcubierre were staggering. To create a warp bubble large enough for a small spacecraft, you would need an amount of negative energy equivalent to the total mass energy of the planet Jupiter. Later, refinements to the theory playing with the geometry of the warp bubble managed to reduce this requirement significantly, but the reduction was from astronomically impossible to merely colossally impossible. Even the most optimistic models require converting the mass of a large planet into a state of matter we do not know how to create or contain. The fuel tank for your starship would need to outweigh a world. But let's engage in a flight of fancy. Let us assume that some future civilization masters this energy problem. They learn to generate and control vast fields of negative energy. They build their first warp ship. They stand at the precipice of the stars. Even then, they would face a cascade of bizarre and deadly paradoxes. The first is the horizon problem. The very nature of the warp bubble creates a kind of event horizon both in front of and behind the ship. The pilot inside the bubble is causally disconnected from the outside universe. You could not send a signal out from the bubble. Nothing from the outside could get in. This means you cannot see where you are going. You are flying completely blind. Any light from your destination would be unable to reach you as you are in effect outrunning it within your space-time wave. You would have to have calculated your entire journey with perfect precision before you even began, because once you engage the drive, you can't steer, you can't change course, and critically, you cannot decide when to stop. You are a blind god in a runaway universe of your own making. Then there is the creation problem. To initiate the warp bubble, you must first distribute the exotic matter around your stationary vessel. But to arrange this matter in the correct configuration, parts of your field-generating equipment would themselves need to move faster than light. It's a cosmic chicken and egg dilemma. You can't create the warp field without faster than light travel, but you need the warp field for faster than light travel. This suggests that a warp drive can't be started from a standstill. Perhaps it could only be created in pre-existing space-time tunnels, or by some other, even more exotic mechanism, placing it yet another step further from our grasp. But the most terrifying consequence of a warp drive is not what happens during the journey, but what happens at the end. As the bubble moves through space, it interacts with interstellar particles, photons, hydrogen atoms, cosmic dust. Because of the extreme distortion of space-time, these particles cannot enter the bubble, but they can become trapped and accumulate on the leading edge of the wave. They are swept up and imbued with incredible amounts of energy. The longer the journey and the faster the effective speed, the more particles are collected and the more energy they gain. When the drive is finally turned off, when the space-time bubble dissipates, all of this accumulated energy is released in a single devastating blast. A torrent of high-energy gamma rays and particles erupting from your point of arrival. Your ship would emerge unscathed, but anything at your destination, a space station, a colony, an entire planet, could be sterilized or obliterated by your arrival. Your starship is not a vessel of exploration. It is a cosmic battering ram. The act of arriving would annihilate the very thing you came to see. So we stand at another impasse. Wormholes and warp drives, two of the most profound ideas ever conceived by the human mind. Both are born from the deepest, most respected laws of physics we have. Neither violates the local speed of light. They are not science fiction fantasies in the traditional sense. They are mathematical possibilities, extreme solutions to Einstein's equations. And yet both seem to be protected from us by nature, guarded by requirements for impossible energies, by terrifying paradoxes of time and causality, and by consequences so destructive they border on the apocalyptic. It is as if the universe is speaking to us through its equations. It is telling us that the paths may exist, but they are not for us. Not yet, perhaps never. These concepts are not blueprints for future technology. They are cosmic fables written in the language of mathematics. They are stories that teach us about the fundamental nature of reality, about the rigidity of its laws, and the breathtaking imagination required to even conceive of ways to bend them. They force us to confront the possibility that our biology, our form of matter, our place in the universe is fundamentally bound to the slow lane. But the act of conceiving them is in itself a victory. It is a testament to the relentless, unyielding human drive to know. We looked at the seemingly absolute wall of light speed, and instead of admitting defeat, we dreamed of folding the universe in half. We dreamed of surfing the very fabric of reality. These ideas may remain forever on the chalkboard, beautiful equations describing an impossible journey. But they have changed us. They have shown us that space-time is not just a passive backdrop. It is a dynamic, malleable, and mysterious entity. And our destiny among the stars may depend not on building faster engines, but on one day somehow becoming true masters of space and time. The challenge is immense. Perhaps insurmountable, but the dream of the shortcut of the wave remains, a whisper of possibility in the great, silent and boundless dark. We began this odyssey chasing an impossible ghost, a phantom velocity that haunts the dreams of every explorer, the ultimate speed, the final frontier, the speed of light. We have journeyed to the very heart of reality itself. We have stared into the abyss of infinite energy, and we have confronted the fundamental architecture of space-time. Now, at the end of our pursuit, the truth is not a disappointment. It is a revelation more profound than we could have imagined. The finish line we can never cross is not a barrier. It is the very foundation upon which our universe is built. To travel at light speed is not a problem of engineering. It is a paradox, a contradiction in cosmic terms. Remember the relentless equation that governs our motion. As you pour more energy into an object, its mass grows, not in substance but in its stubborn refusal to move faster. Its cosmic inertia swells, becoming a drag against the universe. At first, the resistance is slight, a whisper of defiance. But as you approach the ultimate velocity, it becomes a roar. The energy required spirals upwards, demanding more and more. It becomes an infinite hunger, a debt to the cosmos, a debt that all the energy in the known universe could never repay. You are pushing against a mountain that gains weight with every step, until at the final threshold the mountain becomes the universe itself. This cosmic law is not arbitrary, it is essential. It is the principle that separates yesterday from tomorrow. The speed of light is more than just a velocity. It is the speed of causality. It is the pace at which the universe is allowed to know itself, the absolute rhythm at which one event can influence another. A ripple in a pond cannot arrive before the stone is thrown. A thunderclap cannot be heard before the lightning strikes. This is the inviolable narrative of cause and effect. To shatter the light barrier would be to tear this narrative apart. It would be to create a universe where effects could precede their causes, where a star could be born from the ashes of its own death. It is a realm of pure paradox where logic dissolves into chaos. Our reality is a grand tapestry woven from threads of time and space. The speed of light ensures that the weaving makes sense, that the story of the cosmos can be told in a coherent order. The law isn't a cage. It is the syntax of existence, and so we must accept this beautiful unyielding truth. The universe does not forbid our journey. It simply sets the rules for the voyage. These rules, once understood, do not constrain us. They open up possibilities more staggering than simple speed. They invite us to become masters of space and time itself, for within the laws of relativity lies a strange and powerful gift. A way to cross the unimaginable voids between the stars. It is a promise written into the very fabric of the cosmos, a promise that while we may never break the speed of light, we can bend the universe to our will. Imagine for a moment stepping aboard the starships of our future, vessels not of fantasy but of profound and elegant physics. Your destination is a world orbiting a nearby star, Proxima Centauri 4 light-years away, a chasm of emptiness. At conventional speeds, the journey is a multi-generational crawl, a slow march through darkness spanning thousands of years. But your ship is different. It is a creature of relativity. Its engines ignite not with chemical fire but with controlled fury. Perhaps it is the heart of a miniature sun, a fusion reactor, or the perfected annihilation of matter and its ghostly twin. The acceleration is relentless, a crushing, constant force. Days turn into weeks as you push ever closer to the ultimate speed. 90% of light speed, 95, 99. From Earth, Mission Control watches your progress with agonizing slowness. Years tick by, children grow old, entire generations pass into history. To them, your ship is a ghost, a flickering legend in the deep. But for you inside your vessel, something miraculous occurs. The cosmic clock and the ship's clock no longer agree. Time itself begins to flow at a different rate. This is time dilation, Einstein's most startling prophecy, the universe's compensation for your incredible velocity. For every year that passes for you decades, are vanishing on Earth. The faster you go, the greater the divide becomes. You are voyaging not only through space but into the future. The gulf to Proxima Centauri from your perspective is crossed in months. You arrive a pioneer on a new world, a stranger to your own time. You have paid for your journey not with fuel but with time itself. It is the ultimate sacrifice of the explorer. A one-way ticket to a tomorrow you did not help create. The loved ones you left behind are figures of distant history. This is the profound bargain of relativistic travel. We can touch the stars, but we can never truly go home again. And as time bends for you, so too does space. As your ship accelerates, the universe outside your window transforms. The distance to your destination appears to shrink. This is length contraction relativity's other great secret. The 4-light-year chasm no longer seems so vast. The cosmos ahead of you is compressed in the direction of your travel. It is as if the universe is folding itself to shorten your path. You are not breaking the speed limit. You are simply experiencing a shorter, more compressed reality. The rules remain unbroken, but the playing field has changed. We do not need to move faster than light. We only need to make the distance to the stars shorter, and the universe in its boundless elegance allows for exactly that. This is how humanity will become an interstellar species, not by brute force but by a subtle dance with space and time, by becoming masters of this cosmic ballet. But how will we achieve these extraordinary velocities? What engines will carry us on this relativistic pilgrimage? The answer lies not in a single breakthrough, but in a symphony of them. We will need to command the most powerful forces in nature. We will build ships powered by the very engines of the stars, fusion rockets harnessing the power of a captive sun. Inside their magnetic bottles, hydrogen atoms will be crushed together, forced to merge, releasing a torrent of incandescent energy, a directed stream of plasma hotter than the core of our own sundae. This is not the gentle push of a chemical rocket. This is a continuous, unyielding acceleration. A force that could propel a ship across our solar system in weeks, and over years push it to a significant fraction of light speed. These vessels will be glittering cities in the void, self-sustaining ecosystems on millennial journeys between the stars. Their hearts will be the tamed fire of stellar creation. For journeys that demand even greater performance, we look deeper. We look to the most volatile and efficient fuel source conceivable, a substance so potent it feels like it belongs to magic. Antimatter, the perfect symmetrical opposite of everything we know. When a particle of matter meets its antiparticle, they do not collide. They annihilate. They vanish in a flash of pure energy, a complete conversion of mass into power, 100% efficient. An engine powered by antimatter would be the pinnacle of propulsion. A single gram of this exotic substance could unleash the energy of a bomb. Contained, controlled, and directed, it would be a force of creation. It could push a starship to 99% of light speed and beyond. The challenges are monumental, almost spiritual in their difficulty. How do you create and store something that annihilates on contact? How do you hold a fragment of nothingness in a material cage? The solution lies in fields of pure force, magnetic traps of fiendish complexity. But if we can solve these riddles, the path to the stars is open. We would become true voyagers of the relativistic sea. Yet power is not the only path. There is also elegance. There is the vision of ships with no engines at all, vast gossamer craft drifting on the stellar winds, solar sails kilometers wide but thinner than a sheet of paper, shimmering mirrors of incredible lightness unfurled in the void. They catch the faint but constant pressure of sunlight itself. The gentle rain of photons from our sun becomes a relentless push. It is a slow, patient acceleration, but it never ever stops. Days, months, years, the sail gathers speed, a silent ghost, and we can augment this push. Imagine giant laser arrays stationed in our solar system, beaming colossal columns of focused light across the darkness. These laser beams would strike the sails of small robotic probes, accelerating them with the force of 1,000 suns, pushing them to 20 or 30% of the speed of light. These would be our first true interstellar messengers, tiny emissaries of silicon and steel crossing the void in a single lifetime. They would be our eyes and ears scouting new worlds for us to follow. This is not the thunder of a fusion drive, but the whisper of light itself, a testament to the idea that ingenuity can be as powerful as brute force. And what of the dreams that truly bend the rules, the whispers of warping space, of folding the cosmic fabric? Here we leave the shores of known physics and sail into speculation. The Alcubierre driver warp drive does not propose to break light speed. It proposes something far more audacious to move space itself. It theorizes a bubble of space-time around a ship. This bubble would compress space in front of it and expand it behind. The ship itself would remain perfectly still within its local bubble, but the bubble, this traveling wave of space-time, could move arbitrarily fast. It is a loophole in cosmic law, elegant and breathtaking, but it comes with an impossible price tag. It requires a form of matter with negative mass, negative energy. Exotic matter, something we have never seen and do not know how to create. It may be that the universe forbids such a thing from existing, a natural defense against the paradoxes of faster than light travel. Then there is the concept of the wormhole, an Einstein-Rosen bridge, a theoretical tunnel through space-time, a shortcut connecting two vastly distant points in the universe. Like folding a map in half and punching a hole through it, you would not be traveling faster than light. You would simply be taking a path that is radically shorter. But again, the physics required is staggering. To hold such a tunnel open would require that same exotic matter, a cosmic scaffold made of negative energy to prevent its collapse. These ideas may remain forever on the chalkboard of theorists, or they may be clues, hints of a deeper physics we have yet to grasp. They remind us that even our most fundamental laws might have exceptions, that the universe might be stranger and more wonderful than we know. But they are not our present. They are not our near future. Our path to the stars is the one Einstein illuminated for us. The long, challenging, but ultimately possible road of sublight travel. So we stand at the precipice of a new era of exploration. The impossibility of reaching light speed is not an ending, it is a beginning. It defines the scale and the grandeur of the challenge ahead. It forces us to be more creative, more patient, more ingenious. It imbues our future journeys with a profound sense of meaning. The cosmos is not a small neighborhood we can zip across on a whim. It is a vast, ancient and majestic ocean, and we are just now learning how to build the ships to sail it. This urge to explore is not new. It is encoded in our very being. It is the same spirit that drove our ancestors out of Africa, that pushed them across continents and over frozen land bridges, that built the first ships to brave the terrifying open ocean. Every generation has looked to its horizon and felt the pull of the unknown. Our horizon is now the cosmos itself. The challenges are immeasurably greater, the distances unfathomable. But the human heart that yearns to see what lies beyond is the same. We are redefining what it means to reach for the stars. Our great telescopes are already time machines. The James Webb Space Telescope does not just see distance, it sees time. It peers back 13 billion years to the dawn of the first galaxies. It allows us to touch the universe's infancy with instruments of light. Is this not a form of reaching a connection across cosmic eons? Our robotic probes, our silent explorers, are extensions of our senses. When a rover touches the red dust of Mars, a part of humanity touches it too. When a probe flies through the rings of Saturn, we are there with it. We will send these emissaries first, our scouts, into the great dark. They will pave the way, their journeys measured in decades and centuries. They will show us the wonders that await our descendants. The universe, even within its ultimate speed limit, is not diminished. It remains a place of infinite possibility and boundless wonder. There are more stars in our galaxy than grains of sand on all our beaches, and there are hundreds of billions of other galaxies besides our own. The number of worlds of potential havens for life is beyond counting. We could explore for 1,000,000 years and barely scratch the surface. The speed of light doesn't shrink this frontier, it preserves it. It ensures that there will always be more to discover, always a new shore to aim for, a new mystery to unravel. It makes the universe a worthy challenge for a species with endless curiosity. Look up at the night sky. See the faint, distant light of a star. That light has been traveling for years, maybe centuries, to reach your eyes. It is a message from the past, a postcard from across the void. It is a reminder of the scale of the stage on which we live, and it is an invitation. The universe does not forbid our journey into its depths. It simply asks for our best. It demands our ingenuity, our courage, and our patience. The race is long, the ocean is vast, but the starting line is everywhere we look, and the human spirit is ready to set sail.